Hello everyone and welcome. This short video will summarize an appropriate selection of algorithm and output for predicting the power output of a combined cycle power plant. The details of the environment appear within the original Coursera course project description, so we won't repeat them here. Given that we're attempting to predict power output based upon four features, I've chosen to prioritize the algorithm selection based upon these three criteria. First, accuracy. There may be significant cost impact of an erroneous prediction, as the generating company may incur significant costs from, for example, A, relying upon a peaking power source for excess consumption, that is, underestimating, and B, over-engineering the power production when demand is low, that is, overestimating. Next, computational efficiency. This can impact the consumption of power in an environment that, by definition, we're optimizing for power efficiency. Moreover, while energy companies typically do have access to advanced computational resources, some remote power sites might have limited power and communication resources, for example, SCADA links. Finally, interpretability. Consumers of this data might not be familiar with some of the more complex output metrics, nor should they be. However, they will be quite interested in the relationship between the model and its results, so interpretability is important. With those objectives in mind, an appropriate model would be linear regression using MAPE. In particular, linear regression provides acceptable accuracy and computational efficiency, and MAPE delivers interpretability through a simple average expressed as a percent. While it's true that mean standard error might provide better technical value, given the potential cost impact of outliers, I chose MAPE, prioritizing the interpretability over the financial impact. Here's a view of the Microsoft Excel spreadsheet showing the coefficients of the four factors, as well as the y-intercept. What we see in the calculation is a very strong correlation, that is a large coefficient, for ambient temperature. That's what we would expect because temperature does have a direct impact on the efficiency of output. There's a weak correlation to both vacuum and humidity in the range of 0.2 for both, and a very weak correlation to ambient temperature. To state it another way, the temperature coefficient is in the order of 10 times that of vacuum and humidity and more than 30 times that of pressure. This shows the calculation of the mean absolute percentage error. The percentage was negative, so we show here the absolute value as positive. The result's less than 1/10 of 1%. Of the more than 9,000 samples in the source data, we chose approximately 8,000 as the test set, and then reserved the remaining 1,500 for validation. Initially, we used approximately 100 samples for validation, and this yielded rather good results. An appropriate next step might be to repeat this exercise with k-fold cross-validation. However, that wasn't really feasible using Microsoft Excel, which was the tool that I chose for this exercise. To summarize, I chose linear regression and expressed the output using MAPE. This met our three objectives that we set at the beginning of the exercise. It also has the benefit that linear regression is available using any of the three tools that the course suggested, namely Excel, Python, and AutoML. Thank you for your attention, and good day.